You ready? Good afternoon, everyone. I want to start by thanking everybody for being here today and watching our second part of the presentation. We're going to be speaking a little bit more about our design. This time we're going to talk more about the calculations and anything that has to do with money. So my name is Michael and I'm going to be doing structural with Jacob.
I'm Jacob Khanna. I'll also be doing structural.
I'm Mohammed Al-Tatabari. I'm doing the environmental and the scheduling of the project.
My name is Jeremy Smith, and I'll be taking care of the geotechnical part.
My name is Fabio Ruiz, and I'll be taking care of the drainage design.
My name is Brandon Sansaric. I helped with pavement, aesthetics, and lighting.
My name is Camila Perez, and I did some of the pavement as well.
Alright, so we're going to start with a small overview, a little bit of brief. We're going to have, for the construction factors, alignment, typical section, substructure, and we're pretty much going to run over everything that has to do with the project, even though we already did on the first PowerPoint slide that we had. This one we're going to try to touch a little bit of the topics so you guys can be filled in with these things, okay? So we have substructure, superstructure, drainage design with all the agencies that have to do with it, and a little bit of the design that we chose. We have the transportation, environmental, so it's a little bit of everything within it. Okay, go ahead. Alright, so this is our alignment. We chose, our alignment is a little bit different than what was proposed in the study that we were looking at. We're going to start over here and we're going to come with two overhead bridges, and the overhead bridges are going to be non-stop, segmental from here, and they're going to end here. So they're going to go side by side. Now, because we have so much constraints with space going in the median of A Street, we decided that one of the bridges is going to go in the middle of A Street, and the other one's going to go on the right side of the canal, so on the north side of the canal. So it's the other bridge on this side. And then they're going to come together right here and slowly join together and become one once it gets to here. Okay? So then once it gets here, it's going to drop down, and then you're going to have your regular overpasses every time you get to a major street, such as Miller, 88, even though they're not fully developed yet, because we need to look into the future. Because this is not only a design that's going to be now, it's going to be a design that needs to last a very long time. And all of this one day, we want it to be developed. Go ahead.
Hi again, my name is Jacob. I'm going to be talking to you about the typical sections, some of them. There are many in this project. So as Michael mentioned, we are doing segmental bridge designs for the first 6 miles of this alignment. If Michael can move to the left, please.
Go ahead. Sorry.
These 6 miles include where the extension actually begins, going through A Street, and ending, as you said, here. Those are the 6 miles of segmental bridges. Now, this is your typical section of a single cell box girder segmental bridge. Next slide, please.
Alright, so here, this is what we're going to do for most of the overpasses. Although this one's going through water, so then it's going to look like this. We're actually going through one canal. The rest of them are just going to be overpasses over regular roadways that are not developed yet. The only one that's actually developed is in 88. So around here, 88, this is the only one that's actually developed right now, because it has an entrance to the factory that's over here. The other one, which is Miller, we're going to make it right over here. So that's also another overpass that we're going to do. So for that one, we're going to have a pier on this side, a pier on the other side, and then the girder coming across all the girders. And it'll be just like that. Go ahead.
This right here is a picture of our construction of the segmental bridge. On the top we have a crane, but we really would be using a gantry, which places each segment and uses the existing roadway as a place to build the rest. And the bottom is the completed structure, but towards the end, instead of that, it'll be an embutment. And also, there's going to be 200-foot spans between the piers, and 155 piers at a 20-foot elevation.
Now, I'm going to talk to you about the substructure that we came up with, our calculations that we designed. Since it's not designed yet, we found one similar to what we're planning to do. There's these piers. They're going to be 16 feet, 4 inches by 5 feet thick by 20 feet in elevation. Now, we chose 20 feet because the minimum FDOT requirements is 18 feet for an overpass. And when we have the super elevations, the curvature drops down the height ever so slightly. So we wanted to make the entire thing 20 feet. Now, as you can see here, about 3/4 of the column is not actually 16 feet 4 inches. Those 16 feet 4 inches is at the size of the bottom slab of the box girder. So you'll have the last 5 feet being 16 feet 4 inches, but the first 15 feet being about 12 feet. Next slide, please. Now, as I mentioned, we're having a single cell box girder. These include 24 tendons on the top slab and 12 tendons on the bottom slab. This would be also split in half from the left side and the right side. This is your typical cross section for these slabs. Next slide, please. Now, what we have is a deck that's 43 feet wide. As I mentioned, we're gonna have two separate bridges running parallel down 8th Street. Now, these bridges are gonna include two 12-foot lanes, two 8-foot shoulders, and a 1.5-foot barrier on each end. We're gonna have 9-inch bottom slab and 9-inch top slab with overhangs of about 10 feet. Next slide, please.
Alright, so I did a small cost comparison for all the bridges are going over all the bridges are going over major streets like Miller or 88, or in future expansions it could be even Bird. And what I came up with was I decided to take AASHTO Type 3 versus Florida I-beam. And what I found was that the Florida I-beam was actually a lot stronger based on stability and the overall design of it. So then this is a small cost estimate that I found that it's a 24% increase just by using a Florida I-beam, and it's actually the same strength if you compare it to AASHTO Type 3. So then we decided to go with Florida I-beams for this project. Go ahead. So then we did decide to go with Florida I-beam, but we did our design as AASHTO because we wanted to see an overall comparison of it. So this is Midas 2015. We pretty much drew all of the girders, the slab on top, and it pretty much calculates everything from the tendons and the pre-stressing all the way down to like the supports in every column. So then we're technically doing kind of like a 3-span. We have the first span about 20 feet or something, the second one about 100, which is the actual overpass, and then we have another 20 feet to get to the other side of the roadway. Go ahead. So this is the typical truck that FDOT uses. So that each one of the blue lines signifies like the two sides of the wheels. So then you'll have like here he calculated for 3 lanes. So then each one of these trucks are like they're showing how much it is for an actual like how much it can hold in that location, which is the worst location. Go ahead.
Hello everyone, my name is Fabio Ruiz, and I'll give you a brief rundown of the drainage design. As you can see, the drainage is a little bit more complex and vast, so I'll give you something brief so that everyone can understand it. First of all, one thing that we all have to understand is that jurisdiction on the area falls under the South Florida Water Management District. So every single water quality treatment and storm control has to meet their standards. First of all, Limitless Design has endeavored to create a system that not only maximizes runoff control, but it also maximizes as well the water treatment capabilities. Why? There is currently in the area, there's an ongoing effort to restore the Everglades as well as the wetlands. So we want to help as engineers who want to go along with that effort and not hamper it in any way. Now, our design consists of a system of catch basins, French drain, and detention ponds. The French drain in order to infiltrate the water, and the detention ponds in order to remove pollutants and hold the water. As per our design in general, as per FDOT standard, we decided on a rational method, and in order to calculate this rational method, we use the IDF tables. Florida is in a zone 10, so basically by using rational method, we calculate the total runoff. It's per tributary area, and by calculating this total runoff, we can use then the Manning's equation in order to calculate size the pipes in general. This is a typical exfiltration trench, which is what we are using because we want to go with French drain in general. The reason for the French drain is because we wanted to infiltrate so that after we treat all that water, it could go, we can discharge it back into the wetlands, the surrounding area, the canal basin, because there is an aquifer in the area. We want to help replenish it and combat the saltwater intrusion, which we all know is such a big problem here in Florida. This is what I was talking about right now. This is basically, the aquifers around this area. These are drainage ponds. This is not what we're using. Drainage ponds, we thought about 3 drainage ponds in the area in general. And as per our pipe size, depending on the drainage, on the area in general, but one of the calculations that we did, we got a 24-inch pipe.
Alright, again, my name is Jeremy Smith and I took care of the geotechnical part of the project. And this part of the project, it is showing, obviously we're not correlating with the FDOT standards and whatnot. And during our initial phases, we have to we do our bore samples, that's the first step, and then we do the 10-foot, we want to stay minimum 10 foot with the shallow borings, because if you go 10 feet below that, then you kind of, it's futile, it's not really, it's pointless. And we want to identify significant geotechnical features, and we also want to provide geotechnical engineering information for proposed improvements for the contractors. Next slide, please. And then this is your basic geotechnical, going from step 1 to 2. Again, you do your bore samples, and then we want to do site preps for the construction crew to come in, and so they'll know where and when, or well, they'll know where they'll need to put extra support and where not to, where it will be fine, because there's some areas out there that really don't need much help. Like the sub base is, you can't work on the sub base without properly supporting it. Like that. And that was the scope. Again, really important is the water table. The water table, as we all know here, is next to about 4 feet, but it fluctuates with environmental factors and also with if you're next to areas that have man-made water reservoirs and etc. Okay, on our field investigation, we did the shallow auger borings, and we performed approximately, with the SPT test obviously, with the augmentative borings, and we took the samples back to the lab, and you give the visual inspection, and it was according to the index tests, and we did the sieve analysis, the natural moisture content, and the organic content. Next slide, please. Groundwater again. No, do I? The groundwater was really important during your core samples, because your groundwater is not going to, the samples that are in the borings aren't going to necessarily be accurate, because you have to take the measurements of the water level in your samples, and then you have to also consider that in the actual boring samples the water hasn't fully settled. So it's really important to keep that in mind, because when you're doing your sub-bases and your substructures and whatnot, it's continuously changing. So before you really want to do any constructions before you want to start any construction necessarily, you have to continuously monitor your water levels. Now the embankments. Subsurface conditions for majority of the roadway is on flat land. We have 6 miles that's elevated, and then 8 miles that's actually on flat land. And in those 8 miles, majority of it is just running, a lot of it runs next to chrome, and chrome it has a lot of solid foundation next to it. So that would be the same land we'd be dealing with, because yeah, we'll go out there and we do our necessary, field evaluations, but we also can look back on projects that have already been constructed and use that information with our information, and we will carry on with the construction. Now, designs and solutions. subgrade preparation, it would consist of your, majority of the way again, it would consist of your normal demucking, scraping, grubbing, and your compacting. And some areas will require dewatering. Naturally, it's, you know, it is wetlands. And for that, we would use probably Kelly wells to keep the water out of where we're excavating and whatnot. And we'd also want to try and incorporate surcharging wherever we're laying roadway, because we'd use recycled concrete, and it's environmental friendly. We'll be using something that, you know, is taking up space somewhere else. Now, we'd also use geogrids just for areas that need extra support. FDOT Index 501, and below new base along with the embankment fill, the FDOT Index 505 and 514 with the number 200 sieves. And on side barring potential, it is, well, we would try and do as much side barring as possible, but we're also right next to CMEX Chrome, and that was actually a good, well, it was actually a pro for us because that cuts down on a lot of costs, because the transportation, the hauling from the, you know, hauling limestone for your foundation to your actual job site, it does add up. And we actually found a trucking company that will do $2.25 per ton on top of the aggregate cost, because we're such in so close proximity to the actual plant. Next slide, please. Okay, and then now this is actually really interesting. I found it personally really interesting. Limestone, it is sedimentary rock, and it is prone to erosion by runoff from, you know, the actual runoff from the roads. So there is chance for these substructures, you need foundation. And I came up with, it's a new technique, well, relatively new, it's called jet grouting. And I'll show you some pictures in the later slides, but the jet grouting, it builds the foundation underneath in just a drill shaft, and it is, I personally think it's mind-blowing. And specs for the foot, this is specs for the footing. We're gonna go ahead with, we're gonna have 4 piles, and we're gonna hammer the 4 piles in, and we're going to cap the top of the piles with concrete, and so the whole pile will be 14 by 14. And then the allowable gross load is roughly 400,000 kilonewtons, and it's going to be the FDOT 60 diameter cylinder cones, concrete, pre-stressed. They'll be hammered to a depth of 11 feet, and there will be 2 feet spacings between them, concrete cap, and the frictional resistance from the surrounding soil will be about 600 pounds per foot square, and the point load on the actual substructure will be about 640 kilos. And the base level below the ground level will be 2 feet, below the finished grade there. Next slide. And this is the example of the jet grouting. And now, as you can see, it's a regular drill. The drill will drill down to the specified depth, and then